Okay, welcome back to the IGGM GCPR. This is the sixth talk session. We're going to have 5 talks here. All of them are 5 minutes plus 2-minute questions. If you have any questions, please write them down in the talk session. It's talk 6, and I'll forward them to the speakers. And the first talk is given by Kristijan Kopf, who's going to talk about inline double layer depth estimation with transparent materials. Kristijan, the floor is yours.
Thank you very much for the introduction. Welcome, everybody. I'm going to present our paper, Inline Double Layer Depth Estimation with Transparent Materials. In our paper, we are looking at the task of computing multi-layer depth of a scene with transparent materials. So we have an assumption of a transparent object in front of an opaque background, as can be seen on the right. And what we assume is that we try to compute 2 depth layers, which are selectively single layer or double layer, meaning that we are trying to estimate the closest surface to the camera and the possible second surface underneath for non-Lambertian surfaces, as for example, in the case of transparent materials. So we based our method on an inline acquisition system, which is comprised of a linear transport stage and a scanline, a multi-scanline camera, where each scanline produces a different view. And if we stack this view, we form a 3D light field of the acquired data. So if you consider a simple example as shown here, where we have a coin on top of an opaque background and the clear tape suspended above, we try to compute initial depth estimates from the light field, and we can observe that the slope in the epipolar domain of the light field is directly linked to depth. So by performing an orientation analysis or estimating the slope of the lines, we compute the depth from the light field. So there are multiple methods, and we tried several ones, but we found that structure tensors are suitable very well because they pick up cues from transparent surfaces very well. And this was pioneered by the work of Sven Wanner and Bastian Goldlücke. So if I show you the non-annotated epipolar plane image, you can see that these structures are very faint. So we actually compute 2 models, 2 structure tensor models, one single layer model or single orientation model, and a double orientation or double layer model. And you can see these results are quite noisy and are bound to their respective layer hypotheses, meaning that single layer estimates are only valid in single layer regions, and the same accounts for double orientation or double layer regions. So we came up with the idea of combining all these estimates in a cost volume to rule out weakly supported estimates. And we made the observation that the line angle or orientation in the original input epipolar plane image can be found in the depth estimates as well. So we construct the depth hypothesis resembled by hypothesis rays, and we compute a sum of absolute differences cost, which then forms a cost volume V. So if we look at our previous scene example in this cost volume and we extract a slice from this volume, it might look something like this, where we can see that the structures from the scene can be clearly identified in this slice. So we see the coin, the clear tape, and the background. And from this cost volume, we thus extract 2 surfaces, which was our initial goal. So G1 and G2, which coincide in some regions, but are different in others. Since these results are not smooth enough, we additionally employ a joint TGV regularization, where we formulate a energy and solve it through a primal dual approach, while keeping a global ordering such that one estimate is in front of the other or is closer to the camera than the other. This gives some nice consistent results as shown on the bottom of the slide, where the single layer regions show consistent estimates. In our paper, we show some quantitative as well as qualitative results where the numbers show that our approach is comparable to existing methods, although we only use a fraction of the data. And our qualitative results are based on different industrial use cases, which have been acquired with the aforementioned inline acquisition system. You can see them on the bottom of the screen. So to conclude, we proposed a method for double layer depth estimation in an inline setting. On 3D light fields, we showed how we combine different structure tensor models in a cost volume and extract final double layer results with joint smoothing. Additionally, we showcased some use cases in an industrial setting. And thank you. I'm looking forward to the discussion.
Thank you very much for the talk. As a reminder to the audience, if you have questions, please go to the Discord channel Talk 6 for GCPR and post them there, and we will relay them to the speaker. One thing that I was wondering is, can you think of a way of whether, or can you comment on whether you think you could benefit from using machine learning to some degree? Could it be possible to, for example, try to detect transparent
it's
materials?
Out of the order to come along with a conventional computer vision approach these days, yes. But we actually considered using machine learning in this context, and we've tried approaches on 3D light fields as it is shown here. But the difficult thing with transparent materials is it's not easy to acquire ground truth data. So training on transparent materials is quite difficult. But we are currently looking into generating a data set with ground truth data for transparent materials. So machine learning could be considered for future work.
I mean, nothing is wrong with like classical computer vision papers. I actually write enough of them that I very much appreciate them when I see them. It's just that intuitively, it seems like we humans are good at figuring out whether there's something transparent in the scene because there are certain cues. And I was wondering whether this could help you with your search, like figuring out where in the image you actually might need a second layer.
Yeah, you have to differentiate. As a human, you have a lot of prior knowledge because you have handled some certain objects already in the past. And yeah, conveying this idea to a machine would be a very interesting problem.
Yeah, I agree. This is why I asked. But yeah, thank you very much. Very nice work. Very much enjoyed it. The next talk is by Pham, and he is going to talk about a differentiable convolutional distance transform layer for improved image segmentation. The floor is all yours.
Hi, thanks for the kind introduction, and welcome everyone. We'd like to present a way to incorporate a distance transform layer into deep learning architectures for improved image segmentation, at least where it makes sense. Why is that? In medical image computing, image segmentation and the extraction of anatomical structures is a rather common task. And in the image captioning process, we often follow a rather strict protocol. Thus, in contrast to natural images, we can therefore assume standardized images where structures and especially shapes are similar in between patient images, as you can see in these example CT images. The idea now is to use the distance transform to infer shape information into the training process of deep learning architectures. A distance transform is basically a transform of binary images that assigns each pixel the minimal distance to the next foreground pixel. In this case, we've assigned the foreground pixels as ones. Here we can see the Manhattan distance transform of two toy examples. And as you may see in the binary images here, the foreground shapes in white slightly differ. Thus, when comparing the binary representations, we would only recognize the differences in these two positions. However, when we compare the distance transforms or the representations of the shapes by means of the distance transforms, this small change in shape actually affects the whole landscape. Thus, each pixel in the distance transform contains information about the foreground shape as opposed to the binary representation. That's why we are interested in using the distance transform in deep learning architectures. The problem now is that most distance transform implementations are usually not differentiable. Therefore, related work usually tries to learn the distance transform beforehand to secure the gradient flow during training. We then stumbled upon Karam et al.'s work regarding convolutional distance transforms, which yields a possibility to calculate the distance transform directly by means of convolutions. Oh, here you can see the differences. The main idea is that the distance transform can be approximated by convolutional operation with a specific kernel. The derivation is shown in Karam et al.'s work and is also shortly described in our paper. And the basic idea here is that the kernel here detects every foreground pixel within its receptive field and also calculates its distance to each position to help to approximate the minimal distance to that specific position. There are, however, some problems with this formulation of Karam et al. The first problem that we stumbled upon is that the kernel size actually limits the maximally measurable distance. That's because if we have foreground pixels that are very far away from the current position, the kernel actually needs to cover that foreground pixel with its receptive field. Otherwise, it won't be considered for the calculation of the distance. This also goes with an increase of computational costs. And the second problem is that if we have sparse images where we only have very little foreground pixels, there are very large distances to the next foreground pixel for some pixels. And therefore, this term D gets very large. The exponential term, therefore, gets very close to zero. And the logarithmic term, therefore, gets quite unstable. We can see this on a toy example in which we can see a sparse image where we only have few foreground pixels. Here on the right side, we see the actual Manhattan distance transform. And if we apply that convolutional distance transform, we can see that for far away pixels from the foreground pixels, we don't get any good results. That's why we tried out a workaround with a cascade of local convolutional distance transforms. And the idea is that we now reduce the kernel size to avoid numerical instability. That means, again, that far away foreground pixels cannot be detected by that kernel because the receptive field is too small. And we can only apply local convolutional distance transforms. What we do then to have some kind of workaround is that we iteratively extend the foreground area by non-zero pixels of the current local convolutional distance transform, and we update a global distance transform map by adding the new local distances and an offset to it, because of course the local distance transforms can only calculate very small distances. That's why we need to add that offset to it. Details about this workaround can also be found in our paper. And here you can see in the result of the approximation of this cascade. As you can see, for further away pixels, we can approximate a distance, although it's not quite the same as the original Manhattan distance transform. With this, we can extend a segmentation network, for example, the UNet with the convolutional distance transform, and we can calculate an additional regression loss to infer our shape information. And what should be noted here is that this distance transform does not need to be learned, but can be applied directly. Yeah, we tried that out on a Segthor data set, which is from the Segthor challenge. And we equipped a UNet with that convolutional distance transform layer. And you can see slight improvements in the dye score. And for most organs, except for the aorta. And you can see great improvements regarding house loss distance for the same organs, again, except for the aorta. And we think that these are quite promising results, considering that we are using some kind of distance-based regularization during the training process. And we hope that this is interesting enough for you to take a look at our paper. And thank you for your attention. And I'm happy to answer any questions that may have arisen.
Thank you very much for the interesting talk. One question, if I looked at your results, do you know why the aorta represent, like, why it's harder to get improvements for the aorta?
Mm-hmm. What we need to mention here is, I haven't mentioned it yet, is that we used 2D slices. So we didn't train the network with 3D volumes, but only the axial slices. And in that view, the aorta is rather circular and quite simple to extract. That's why we assume, we aren't 100% sure, of course, but we assume that it's so easy that the UNet already does a pretty good job. And with our additional distance transform, it doesn't get any better results. That's why we need to consider when it actually makes sense to apply this distance transform layer. Yeah.
Maybe as a follow-up, so I like the introduction that you had in the beginning, but in typically what you get is noisy segmentation masks, right? Could you think of a way of making your distance transform more robust to this?
Could you repeat that question? I didn't.
So you had your motivation by saying, if I change the like sign of 2 pixels, then I get different distance transforms, which you could also interpret as, if I make small changes, I might actually get a very different output due to noise. Any ideas on this?
Well, actually, we thought that would be a good option of the distance transform, because what we actually do is we compare the ground truth to our prediction. And we have, if we had a lot of noise in the prediction, that would be penalized even further, even for pixels that are not noise, especially. That was our thought about that. Yeah.
Okay, great. Yeah, thank you very much for the great talk. The next talk is by, and excuse me if I'm butchering your name, Varaha, Karthik, Pattisapu. And it's about PET-guided attention network for segmentation of lung tumors from PET/CT images. Please take it away. We can't hear you at the moment because you seem to be muted. Could you also activate your camera?
Yeah, hi. So,
Great.
am I audible now?
Yes, we can hear you.
Yeah.
Please start.
Good morning, everyone, and welcome to my talk. So I'm a master's student at ETH, and this work is a part of my master's thesis at ETH. So, yeah. So as we understand, PET-CT imaging is quite vital to the diagnosis of lung cancer, and each of the two imaging modalities provide usually complementary information regarding the state of tumors. However, oftentimes we have only a combination of CT and PET-CT images. So PET-CT images are usually only a few in number in comparison to the CT images due to various economic and logistic reasons. So as a result, we end up having only a pool of PET-CT images and CT only images for which PET images are unavailable. So this poses a very challenging scenario. The conventional models can only process either the CT or the PET-CT images, but not a combination of both. For example, here the conventional model A can only process the CT only data, but not the PET-CT data, and the model B can only process the PET-CT data, but not CT only data. So as a result, the effective data that these can process is greatly reduced when there are only a few PET-CT images in comparison to CT-only images. Further, it is also unclear how the models that do process a combination of these CT-only data and PET-CT data can actually make its efficient use. So the question remains how to make the efficient use of CT and PET-CT data. So we want to come up with a model that can actually make the best use, the efficient use of both the scenarios, right? So to that end, we propose to tweak the attention mechanism of an already proposed model attention unit. So an attention unit is the same as a unit architecture, but with the addition of what are known as these attention gates. An attention gate learns attention masks that learn, important regions of the input feature representation. And this whole learning process is usually guided by a context signal. So in our particular formulation, we introduced a new composite function h of x, which more or less acts like a switch. So when PET images are actually available, we extract some important features from through this function h of x. And so the information from this composite function basically complements the context signal, as PET images can provide additional context to the malignant regions that are of particular interest. So basically this attention gauge, so the introduction of this composite function more or less aids the attention process, the learning of the attention process. So, but our formulation of this composite function is not just restricted to being a switch. Because of the flexibility that it allows, our model can be trained on a pool of CT only and PET-CT images. So basically we can then use, a combination of CT and PET-CT images. The figures that shown here demonstrate this particular flexibility of the model. The figure shows the dice coefficient of the proposed model, which is highlighted in blue, with respect to a conventional model, which is highlighted in red, as the ratio of the PET images is increased from 0 to 1, keeping the number of CT images fixed, of course. So that means it can be seen in the leftmost region where the ratio is quite small, or in other words, the PET images are few in comparison to the CT images. Our particular model is, able to perform much better than the conventional model. So basically meaning which our model is able to make the efficient use of the complete available data, that is the CT images and the PET-CT images combined. So in conclusion, we note that due to a variety of reasons, PET-CT images are scarce in comparison to CT-only images. So while conventional models are, unable to make the efficient use of a combination of both, we were able to do so with our proposed model. And we were able to do so with the introduction of what this attention mechanism or in our model. Yeah, and that's it from my side. And any questions?
Thank you very much for the interesting talk. I was wondering whether you compared your method against some ensemble method where you train one method on PET scans and one on CT scans. Do you know how this combines?
I mean, I couldn't get you. Are you referring to this particular figure here, or?
You could think of training one network on one type of data and another network on the other type of data. And if you have both of them, then you can make.
Yeah, so basically that means we have two different models, right? So basically what our approach was that basically to integrate both the two scenarios in one model. But what is the use? The use case is that you can actually train with 100 CT images and 10 PET-CT images. And that kind of training scenario wouldn't be possible with by having two different models, right? So.
Okay, yeah, great. Thank you very much. And as a reminder for the audience, if you want to ask questions to the speakers, please post them in the Discord channel. Okay, our next speaker, and again, sorry if I mispronounce your name, is Imant Daunhawer, who's going to talk about self-supervised disentanglement of modality-specific and shared factors improves multimodal generative models. Please take it away. And Varaha, if you could mute yourself and disable your video. Thanks.
Thanks a lot for the introduction. By the way, name was perfectly pronounced. Thanks for that. So we present the disentangling multimodal VAE, which is a new multimodal generative model that disentangles modality-specific and shared factors in a self-supervised fashion. A multimodal generative model, such as a multimodal VAE, learns a joint distribution over a set of input modalities, x1 up to xm, and ideally it should be able to handle many-to-many inference and many-to-many conditional generation. In simple words, it should be able to deal with missing modalities. Here's an overview of the proposed method. In a nutshell, it splits the latent space into shared and modality-specific subspaces and learns to disentangle these subspaces with suitable information theoretic objectives. On the left-hand side, you see the encoder. For the input x1, the model encodes it into a modality-specific representation S1 and into a shared representation C, which is aggregated across modalities using a product of experts. This is based on previous work, and it allows the efficient aggregation of representations from any subset of modalities. On the right-hand side, you see the decoder. There's really nothing fancy here. We just concatenate the shared and modality-specific representations and reconstruct the observation XM. This is the variation autoencoder part of the loss, or one part of that. In addition to that, we have two objectives for the disentanglement. First, the shared loss, which maximizes the mutual information between different subsets of modalities and thereby learns to encode shared factors. Secondly, we have the disentanglement loss, which minimizes the statistical dependence between subspaces in an asymmetric way, which just means that it regularizes out shared information from the modality-specific subspace SM. But really, the key difference to previous work is that we take a multimodal VAE and add the latent space split plus the disentanglement. We use two toy experiments to validate our approach. First, we have the MNIST SVHN dataset, which is an existing benchmark introduced in previous work. On the right, you see how this data set looks like. It basically consists of pairs of images from the MNIST and SVHN data sets paired by digit labels. It is very convenient in that it allows to evaluate the semantic coherence of the generated images. Second, we have the paired MNIST dataset, which is based on a similar idea, but it goes beyond two modalities. Even though we use MNIST a bunch of times, we shuffle the paired images such that we combine images of different writing styles. Further, we add a Gaussian noise to make the problem of recognizing digits a bit more difficult. In the interest of time, I will only present the results for the MNIST SVHN dataset. So using similar encoder and decoder architectures across methods, the proposed model performs significantly better than previous work. Here we measure the following metrics. On the left, the linear classification accuracy on the latent representations. On the right, the semantic coherence of unconditionally and conditionally generated samples. Not only does the proposed model better preserve the semantics, but it also generates images of comparable or higher quality, as we can see here in terms of FIDs. As an additional benefit, the DMVAE allows sampling from modality-specific priors, keeping shared factors or shared information constant. Here you see how different models generate SVHN digits given the respective MNIST digit from the first row. Notably, only our method can keep consistent styles across counts. Summarizing our contribution, we introduce a new multimodal VAE, which splits the latent space and disentangles shared and modality-specific factors. Empirically, it shows an improved performance on a set of toy problems, and additionally, it allows sampling from modality-specific priors. Thanks a lot for your attention.
Thank you very much for the great talk. It's very interesting work. One thing that we noticed at some point is that all those generative models that go through latent space are actually quite able to hide details in the latent space, such as on modalities, on imaging conditions. And I wondered whether you observed something similar for your method. So is it hard to find a good latent space dimensionality, or is it robust to that?
Do I understand the question correctly, that you say that, for instance, the images, because they become blurry or something, which is typical for VAEs, they hide some details? Or do you really say there are semantics in the input image that just don't appear, even if they are very, very visible?
So the question is, what we have seen is that if your latent space is okay, I'm back. Sorry, my internet connection is a bit unstable today. What I was saying is, if your latent space dimension is large enough, then that encourages the network to store information there that you don't want to have stored there. On the other side, if you make the latent space, so it doesn't seem to be that easy to just like reduce latent space dimensionality, because at least some models seem to really need to store those details there that you actually don't want in there. Did you observe something similar?
That's a very interesting question. To be honest, our ablations didn't go as far as really test a lot of different dimensionalities. We rather used the models that previous work was based on and stick to those architectures and just try to add those additional loss terms. But I think it would be very interesting to ablate in this regard as well.
Thanks. And there's a question from Discord. Have you also tried combining more radically different modalities, so images and audio or text data?
Yes, that's a very interesting question. Thanks for that. That's something we're currently working on. I mean, that's the end goal of it. Of course, we only show toy data sets here, and there's some additional problems that come with that. So one is that if you have many modalities, the dependencies between those can become more complex, right? Here we observed that the images had a set of shared factors across all modalities, and that becomes much more difficult and much less controllable when you have very diverse modalities.
Thank you very much, and thanks for the great talk. The last speaker in this session is Kristijan Fugošić, who's going to talk about multimodal semantic forecasting based on conditional generation of future features. Yeah, the floor is all yours.
Thank you for your introduction. My name is Kristijan, and I will present our paper. So our biggest motivation was in scenarios where some previously unseen space was unoccluded. For example, when we are turning around the corner, or when some other vehicle passes by and reveals space behind it. And because of that, we wanted to give our model opportunity to generate multiple different futures while taking into all possible scenarios. So we do that by converting baseline feature-to-feature model into a conditional generative adversarial model. On the left side, you can see Oracle, which we use to train feature extractor and AMP sampling branch, and we also use it as an upper performance limit. And on the right side is our model's architecture. So we use a feature-to-feature model as a generator in a red rectangle, and we use modified PageGAN as a discriminator. We now generate multiple features, and we apply adversarial loss, and in addition, we also apply moment reconstruction losses to combat mode collapse. So shortly about those MR losses, we calculate mean and variance on k different predictions. And instead of applying a loss function directly on individual predictions, we apply it on those moments. And now we have MR1, which takes into account only mean, and MR2, which takes both into account. And I will preview our results. So for accuracy measure, we use mean intersection over unit and mean intersection over unit on movable objects. And for diversity, we use mean square error and LPIPs. So with MR1, we observe slightly higher accuracy, but with MR2, we see slightly lower accuracy, but higher variance, as we will see moments later. And on this table, I compare top 5%, meaning best prediction out of 20 generated with ensemble. And we can see that MR1 does indeed generate predictions of higher quality, while MR2 fails to beat the ensemble. So let's take a look at some examples. Across these scenes, we see slight improvement in accuracy, along with some multimodality in highlighted areas. So let's look at this third scene. We see better performance around this bike and person. And in fourth scene, we see multimodality around this person on a scooter. Somewhere it is recognized, somewhere it is not. We will see what we get when we look at the MR2 results. We also see multimodality in that same area, but person is better recognized here, for example. And first scene is especially interesting because when this car passes by, in first frame, we see people, but in the last frame that model observed, it didn't see people. But it correctly predicted that in this case, people will indeed be behind a car after it passes by. In midterm predictions, we can also take a look at last scene, where this is best as of yet prediction of a distant person here. And we also see better performance when we look at this bike, which is smudged in baseline model, and it's somewhat nice on our results. And with MR2, we see greater diversity, but it also results in more catastrophic scenarios results. We also proposed a new metric So with full line, we see pixels that were correctly classified at least once through multiple forecasts, and with dashed lines, we represent a line. That line represents best individual result as of yet. So we can also compare here MR2 and MR1. We see that MR2 goes higher and it goes faster. And midterm also results in greater multimodality as was expected. So in conclusion, we achieve accuracy that is comparable to the base model. We see visually interesting and diverse results, and our model often accepts to take a chance on dynamic and small objects. Training is a bit longer, but inference is similar to the baseline. Thank you.
Great, thank you very much for the interesting talk. One thing that I was wondering is that, so there were multiple talks at this conferences mentioning the advantages of flow, normalized flow, to be able to actually sample from like the complete distribution, which seems could be advantageous in your case scenario because the future obviously is uncertain, so you might want to sample over multiple predictions. Did you look into this? I know that it's a recent topic, but I was just wondering.
Yes, it's a bit different approach from ours. I did look into it, but well, there is still a lot of possibilities on this problem. We can use different generative models, different discriminators, we can use instance segmentation instead of semantic segmentation. So yeah.
Yeah, thank you. I think this concludes the live talk, live part of the session. The session itself continues until 12:30, so you have ample time to discuss with the authors on the Discord channel. This was actually also the last session with contributed papers for DHM GCPR. We will have two more events today. The one first is the joint keynote by Hans Christian Hege on Human Against Virus, New Needs for Visual Computing and Visual Communication, which will happen between 2 and 3 p.m. And then the awards and closing ceremony, which starts at 3. With this, I would like to thank all speakers in the session for their great talks and for submitting their papers, contributing papers to DHM GCPR. And yeah, hope to see you all later in the remaining sessions. Thank you very much and see you later.